goes here? 1 or 2 or 1/2? Exactly. A 1, so, or nothing. So again, here's your reminder, R1 is equal to R1A over -1, which is equal to R1B over 1, right? Everybody remember that equation from the first day of class? If you don't, it was there. That is equal to K1 CA, which is also equal to K1A CA. Why are these the same essentially? Because this is a 1. Now let's do the same thing for reaction 2. R2A over what? Which is also equal to R2C. I lost my space, yeah. Over 1. Which is equal to, damn it, I keep losing my space. There we go. K2 CA squared, which is also equal to K2A over 2 CA squared. Okay, so let's keep looking at these equations and let's write down R1A is equal to what? In terms of the K1A, the one on the far right. Negative K1A CA. And what about R2A? Again, in terms of the rate constant defined with respect to A, because that's what we're given, K1A and K2A. So that's how we're going to define our rate equation. Yeah, we'll write it that way, that's fine. Negative, it's -2 times K2A over 2 CA squared. The 2's cancel, negative K2A CA squared. Any questions about that? Okay, I know that can be confusing. All right, so we've got our rate equations now for the first reaction in terms of A and the second reaction in terms of A. And now let's finish off our material balances. But don't forget that those are there. We're going to get rid of this because it's not helping us. When we do these material balances, we're going to write things in terms of the rate constants where we're given information. So K1A and K2A, not just K1 and K2. All right, so that means that the rate of production of A is equal to what? Negative K1A CA minus or plus. No, that's the rate of production, so it's a minus.
But we just wrote R1A equals
R1A equals negative K1A, so.
Damn it, did I write that down? Why? Yeah, so, sorry. That was the wrong part. What I wrote down was correct. This should not be like that. This is the rate of production, so I shouldn't write the rate of consumption in the very next step. So this should just be R1A plus R2A. And now that's negative K1A, concentration of A, minus K2A, concentration of A squared. Does that make sense to everybody? I wrote the rate of production and then I wrote it equal to 2 rate of consumption, which wouldn't have made much sense. All right, now for B, it's the net rate of production of B. So what is that? The rate of production of B in reaction 1. Don't have to worry about reaction 2, and that is equal to K1A CA.
Why isn't there 1/2 in that? Roughly?
Which one?
The, which is minus K2A CA squared. Why isn't there 1/2 there? Let's see.
Because this is equal to K2A CA squared. We're defining things in terms of the little k, the K2A and the K2. If it was K2, then I would need it. Except then it'd be 2 times. Yeah, I mean, I'll put that up here for reference, but don't let it confuse you guys. This will be K1 minus 2 times K2 CA squared. So I'm consuming 2 A's every time I do that second reaction. All right, so this is this one, which is also equal to just K1 CA. And now D FC dV, the rate of C, which is equal to the rate of C in reaction 2. There is no reaction 1. And that is equal to minus 1/2 the rate of 2A. So you get K2A CA squared over 2, which is also K2 CA squared. Again, the one that we're going to use for this problem is this one because we were given information about K1A and K2A. All right, so those are my material balances and my rate equations. What comes after that? Concentration of A. So what you use for multiple reactions in the gas phase is this form. Concentration of A is equal to the total concentration times the flow rate of A divided by the total flow rate times P over P naught times T naught over T. Okay? If you don't remember, that's in the chapter on multiple reactions. Again, we don't want to put things in terms of conversion. So we're not going to put 1 plus epsilon x this time around. Now, we're going to neglect delta P. So this goes away. And the concentration of B is equal to what? The initial total concentration, flow rate of B over the total flow rate, T naught over T. And of course, you get the same thing for C, except it's the flow rate of C over the total flow rate. And what is the total flow rate? Since we're using that in these equations, it wasn't given to us, so what is it?
CA naught plus C.
It is P naught divided by RT naught. Are you given the initial pressure? All right, so that's not helpful.
CA naught plus CV naught plus C naught.
Yeah, sure.
But we're not getting the either.
So flows divided by the,
What's the feed?
isn't just pure P equals FA plus.
Pure A is the feed. These go away. Were we given the initial concentration of A? Okay, so we're done. You can also define it as the total concentration times the initial molar fraction of A is equal to Ca naught, right? And again, this is pure. So that goes away. So that's just one. All right, another equation that we're going to use we're using total flow, so what is total flow?
Flow bit. Oh wait, no, it goes up to each of those.
If we had inerts, so it would be in there.
Can you say something about the coefficient or
What's that?
something? The total concentration that, coefficients inside of it, but total flow rate remains the same.
The total flow rate would change, it would have
In terms of
coefficients
A,
if I were writing it in terms of A, but I'm not, right? So it's just the total flow rate of all species. Okay, some other things that I just want to remind you guys of before we switch to Excel is some definitions related to multiple reactions. So what is the instantaneous selectivity? Anybody remember? Yeah, so let's put B over C, rate of B over rate of C. What is the overall selectivity? This SB over C with a hat, and that's just the flow rate out of B divided by the flow rate out of C. All right, so that's our selectivities. What about instantaneous yield? Anybody remember that one?
RB plus RC divided by negative RA.
That would be the yield of all species. We just want the yield of a single species. So YB is going to be the rate of B divided by the consumption rate of A. And then overall yield also has the hat. And what's that going to be equal to? FB, not negative FA. Yeah, FAO minus FA. And what is that denominator?
The amount being converted.
Yeah, it's the amount of A consumed, right? That's how you can think about it. It's the amount of A consumed. All right, so those are our definitions for various crap. Okay, so we've got 1, 2, 3 differential equations.